Alright, I'm back. So this is still 1.1, but I'm just part 2, I guess, now. So we're going to do another distance and displacement calculation. So we want to figure out what's the distance from A to B to C. And I didn't really talk to you about this, but I think you can figure it out because you guys are all very intelligent. And then we're going to calculate the displacement from A to C, or from the initial point to the final point, which is what we're going to call R. So we're starting here at point A, and we end up here at point C. And I didn't talk to you about how to do this, so it's kind of just using some maybe some math skills that you might have already in your bag of tricks. But we're trying to figure out the distance first. So the distance is just the lengths, you just add them together. So we start at A, we're going from A to B, and then we're going from B to C. So if I asked you how far you had to travel, if like you were walking along campus and you followed this path, and I said, how far did you walk total? What would your smartwatch say? How many steps did you take? That's kind of what we're talking about here. So the distance total, I'm going to try to type a little bit here instead of relying on the pen, because I think that it'll be easier for you guys to see. So the distance total would be 3 meters plus 4 meters. So 3 plus 4 is just 7 meters. So again, that's it. You're just adding the length. So this is 3 steps, maybe in 4 steps, so you get a total of 7 steps. For the displacement, it is a little harder. And the reason why it's a little more challenging is because it's not just in a straight line. So we're moving in multiple directions here. And I want to know the displacement. Again, displacement is from where you start to where you finish. So we're starting at A, we're going to C. So we're looking for this path, this green kind of path. And remember, displacement tells you a direction. So if we start here, we're going kind of different thing. Sorry, there we go. We're going in this direction, so we're going kind of from up and to the right. But I just asked for the magnitude, so the magnitude is just the amount. So if you look at this shape, how can I figure out this green side of this shape? So what shape is it? It's a triangle. And hopefully you guys are familiar with the Pythagorean theorem. So we're going to figure out the idea using the Pythagorean theorem. I'm going to write this because it's got some squares in it. So I would do this length AB, which is amount 3 squared.
That's what I was asking.
Plus the length of BC here, that length of the triangle, which is 4 squared. And that's equal to what I call this hypotenuse side, R squared. Hopefully you guys remember some right triangle trig. If not, we will review it and you'll get better at it and remember it again. So we want R, we want that length, so I'm just going to take a square root. Displacement, so I'm going to take a square root. So 3 squared is 9, 4 squared is 16, so it's the square root of 25. And you guys might remember, depending on your math teacher, that the square root of 25 for R is going to be 5 meters. So it's kind of like taking the shortcut path. So this path is less than these 2 paths added together. So this is R, so 5 meters is what you should get for that. So that's the Pythagorean theorem. This is a 3, 4, 5 triangle. All right. Yeah, I should have just clicked on the screen because it had all the answers there. Continuing on, so we've discussed distance and displacement. Let me pause a second here and kind of go back. And talk about the differences between these 2 ideas. So distance, make sure you write this down. Distance is the space between points. It's kind of a length. It's a number of steps. And it is what's called a scalar measurement, where displacement is the change in position. And with change in position, you just care about where from start to finish. So you always go from where you start to where you finish. It's the difference between those 2 points. In the last example we had multiple directions, so we had to do a little bit more complicated math. But in one-dimensional stuff, it's just the change in, so you're just subtracting. Go back over here and take this measurement as well. Nope. Finally. So this is what's called a vector quantity. And a scalar measurement, all you need to have a scalar measurement is a number, so the amount, so whatever that space is, a number and a unit. And for a vector, it's a little bit different. So a vector quantity, you need a number, a unit, and a direction. So kind of going up and to the right. So the number is called the magnitude. That's just a fancy word for that. Usually the direction we indicate with, in our math problems, we indicate it with a positive or a negative. So that is the big difference between a scalar and a vector quantity. This is important. You want to make sure that you start to get this in your head. Distance is a scalar measurement. Displacement is a vector measurement. We're going to talk about velocity and speed next on this slide, and they're different as well. They're very similar. Kind of in your everyday life, you would use different words to describe those. You would say speed and velocity are the same thing. In physics class, they are not. Velocity measures the rate of displacement, or how quickly you change your position. It is a vector quantity because it's dealing with displacement. Speed is the rate at which a distance is covered. So that's distance over time versus displacement over time. So again, the subtle difference between distance and displacement is the same subtle difference between speed and velocity. Velocity is a vector, speed is a scale. So if we look at these for speed, you take the distance traveled divided by the time. So this would be, it goes 40 meters in 1 second. And for the bicycle, it goes 20 meters in 1 second. So they have different speeds. They also have different velocities because they have different displacements in that 1 second of time. But you would just divide. So it would be 40 divided by 1 and 20 divided by 1. And you'd get 40 meters per second. Or sorry, feet per second. And then, because the unit's feet. And then for the bike, it's going at 20 feet per second. So that would be 20 feet per second would be its speed. For velocities, they would actually be the same values. So this would be 40 feet per second going to the right, or positive 40 feet per second. For the bicycle, it would be positive 20 feet per second. So sometimes the speed and velocity aren't that different. Other times they are very different. Okay. So again, speed measures only how fast an object moves, but velocity tells us kind of its speed and direction. So again, I don't love this definition, but it's the way that the book defines it. So it's on this slide. So first off, for bike 1, it says bike 1 is moving to the right. If we look at this, it travels 20 feet in 1 second, and it's going at a constant. Bike 2 is moving to the left at, it looks like it's covering negative 20 feet per second, so that would be negative 20 feet per second. So again, the difference here for bike 1, sorry, trying to get a pen that works. That's a positive 20 feet per second, because it's the displacement, which would be that displacement is positive 20 going to the right, so that's why it's positive. This one would be a negative 20 because it's going to the left, so that's negative. This one's positive. So bike 2 has a negative 20 feet per second. So again, that positive and negative is a very important descriptor. It tells you the direction that you're moving, which is essential to describing vectors and motion correctly. If we asked what's their speeds, they actually have the same speed, because the speed is the amount of space covered in the time, so they both cover 20 feet per second, but the positive and negative again tell you the displacement and the direction. All right, so let's try this example with this dog Frank. I just googled Frank on the internet, and this is an image that came up, so I used it. So it says at 12 seconds, Frank is at a position of 25 meters. 5 seconds later, he is at 20 meters, and we want to know what's Frank's velocity. They give you some extraneous information, so sometimes in a problem they'll just give you facts that you don't really know. To find the velocity, we need the displacement, so change in position over the change in time. And that's what our velocity is for Frank. He's moving at a constant rate. So his displacement, he's going this way. So he starts at 25 and he goes to 20, so final minus initial. So that would be, final is the 20. The initial is 25. We would subtract them. So if we take 20 minus 25, we get negative 5 meters. So negative 5 meters is the displacement. In the time, it is 5 seconds. So if we divide 5 by 5, we get -1 meter per second. And that checks out because we move to the left. The displacement is going to the left, so the velocity is going left. So again, if you have a positive or negative in front of velocities, that positive or negative doesn't tell you if it's speeding up or slowing down. It just tells you the direction in which it's moving. All right. So that's important. On your Google slide, you can remove this image of Frank, remove them, and you can get to the actual answer, and that's kind of worked out for you there. All right. So we're getting towards the end. Scalars and vectors. We've touched on already. So a scalar is described by a single number with a unit, vector, a number, unit, and direction. So again, the magnitude is the number, that's the size. The direction is associated with the arrow, that velocity. So we draw pictures of vector quantities with arrows pointing. So as you can see, here's displacement vector. We again kind of touched on this already. So if we had Sam, and the distance that Sam would travel is this length or space between those. The displacement is the arrow. Okay. So again, that direction, Sam is just moving to the right. We've done two-dimensional one when we did the triangle problem. This is Jane. Jane starting here and finishing here. So again, we would maybe use some trig, but the displacement is always from start to finish. So that arrow points at where she starts, the initial position, and then the final position. Velocity vectors, again, are just arrows that represent the displacement, a rate of displacement, about a rate of displacement, which is the displacement divided by the time. That's our definition of velocity, and in the direction. So we can look at these two. Longer arrows mean going with a greater velocity. So just to end and conclude, we did the particle model, and we said that we're going to represent more complicated objects just with dots, and every dot is spaced in the same unit of time. So if we're using seconds, each dot represents 1 second of time, and the space between those dots shows you the amount of length traveled. If you're going from one dot to another, the direction between those dots can be established, and you can figure out the displacement. And from displacement and time, or distance and time values, you can measure speed and velocity. Again, scalar measures only represented by a number and a unit. Vector measurements are represented by a number, a unit, and a direction. Magnitude is the amount or number part. Velocity vectors we draw to help understand that direction better. And then finally, position and displacement and distance, those ideas, we use our coordinate system to figure those out. So I'll stop there. Hopefully this was helpful, and if you have any questions, just make sure you ask.